forward. Okay, so today we're going to look at two different things. We're going to be looking at how to graph logarithms, and we're also going to look at what the properties of logs are, which is actually something we haven't gotten to yet. What we did so far was kind of weird and complicated, but there's a reason why Napier invented it, because back in the day, what you may not realize is, well, I think any of you had me or you had Wheeler, when you did trigonometry, did any of you guys get a piece of paper that had all the signs listed, the sines, the cosines, and the tangents? Did any of you get that? So instead of using a calculator, you could look at the table and you could find the list? Yeah, that's actually in the old school, that's how they would do that, is they'd literally have a list and you just kind of cross-reference. And so if you wanted the sine of 27 degrees, you'd pull out your little list, you'd find sine, you'd find 27, you'd go get it, because these things didn't exist, but they had tables that had all those things in. And so logarithms used to have a lot of tables as well. And so I'll kind of explain how that works. So what I wanted to look at today with you guys for a couple of minutes is graphing. So you can graph, we'll just make a rough sketch on paper. You don't literally have to have graph paper to do that. And let's kind of see how that plays out. So let's just suppose that we started with this idea right here. And this is just my own style. So please understand, this is how I personally like to do these problems. Are there other approaches? Without question, there are. But this is kind of the way that I would like to look at it. I have twice the log base 3 of x minus 4. And one of the reasons I spend so much time on graphing by transformations is by the time you reach this level, you should know a bunch of stuff. Even if you have no clue, which you probably don't, what a log looks like, I know that whatever that log is, what happened to it? What happened to it right here? It got moved to the right 4. Whatever that object is, it got moved to the right 4. All of the x values got kicked over. What did all the y values do? They got multiplied by 2. So here's my process. What's the base of that log? 3. So here's what I do. Step 1. I just go over here and I write the wrong question. I need you to understand that's the wrong question. It's not really 3 to x. That's an exponential. That's not a log. But I think everybody in here probably knows a couple of nice, easy values I could graph if it's a log. If it was an exponential, excuse me. I think I had to use these 3 values pretty universally, didn't we? Was that pretty simple? And so 2 gave me 9, 0 gave me 1, this one gave me 1/9, and exponentials always had that. So far, is everybody doing all right? So please understand, I am not at all telling you that this and this are the same. I'm not. I'm answering this question because it's easier. Here's what I'm going to do. Now I'm going to change it to the log base 3 of x. And the connection that I was trying to make with you guys yesterday is that a log and an exponential are inverses of each other. In fact, that's how we developed this idea yesterday. What did I do to all the x's and y's to turn it from an exponential to a logarithm? Switched them. That was it. Now that I'm here, now I know a lot of teachers would tell you to go a little faster road, but can you guys all do that pretty quickly without really hurting yourself mentally? Was it hard to flip them? No. Oh, geez, that was easy. And then, so what am I going to do? My final idea, if I'm going to fix it, is I'm going to move all of the x values over exactly 4. I move them all over 4. What am I going to do to all my y values? I'm going to multiply them all by 2. So what happened to this asymptote that used to be at x equals 0? Where is it now? It's at x equals 4, and I'm done. So let's see what our graph looks like. So I've got a vertical asymptote at x equals 4 right here. Please, please make sure you include your asymptote. X equals 4. 4 and 1/9, which is, where the heck is 4 and 1/9? Isn't it like really super close to 4? So it's like super close to 4, and it goes down, way down here. I'm going to call this one A. And then 5 was 0. I'll call this one B. And 13 is going to be 4. It's going to be way the heck out here. Again, I'm being a little bit less formal about this because 13 gives me 4 is way the heck out here. And we talked about this yesterday. Why did it take so long to get out there? It's because the original exponent was really steep, and so this is really, really flat. So let's see if we can see how we did by looking very quickly here at Desmos. So let's do a new share. Let's pop over this. So everybody, let's pop this thing into Desmos and see how we did. I made a little table. So I think it would be worthwhile to plug those in. I had 4 1/9, which is like, what, 37 ninths. Gave me -4. Oop, 37 ninths. Gave me -4. I had 5, gave me 0. I had 13, gave me 4. Now, unfortunately, that doesn't show up on the screen particularly well. And I had x equals 4 as an asymptote, which we have discussed that should be dotted, right? So now, where am I going to find that fancy little log button? Remember, I told you there's a place in here where it will graph logs for me. We go over to keyboard, functions, miscellaneous, and there it is. So, I just messed mine up. So we had log base 3. We had x minus 4, and you can see, I don't know why that was there, but, oh, I do know why it was there. I accidentally typed over the top of something that I already had, didn't I? Let's take this, I'm going to cut it and put it down here below. That's better. So, and then there was supposed to be a 2 in front, wasn't there? How do we do? Did the graph nail it like I wanted it to? So, again, was this crazy, crazy difficult to start with an exponential and turn it into a log? I'm hoping it's not that bad. So can you guys do one with me and just see if you can hang with it, and then I'd like to kind of move on, okay? I don't want to go too fast, so please let me know if I'm going too quickly. And so I'm going to go with something really super easy. I'm going to go with a base 2. Let's go 3 minus x plus 1. Now that's actually about as hard of a problem as I could give you because I just messed with you more than just a little teeny bit. Could somebody tell me what I've really tried to encourage you to be aware of that I did right in here? What did I do? I added a negative to the x, and what do we say not to ever do? Never let anything be attached to that x, right? So what I'm going to do is let's rewrite this, put that negative on the outside. Cooper, can you tell me what needs to go in here so this still says 3 minus x, but it looks better? So this x should be negative, shouldn't it? So that's this. Still says negative x. But it needs to be a positive 3, so what has to go here? If I write a plus 3, what happens when I distribute this negative? It becomes, so if I did a negative 3, then what happens when I distribute the negative is I have a negative x and I have a positive 3, which is what I have. So, again, different people do this differently. I'm going to start with 2 to the x. So again, my take. You may look at videos, you may talk to other people that do this slightly differently than I do, but I always start with the exponential because I find that to be very, very simple. The exponential is nice. Okay, let's see if we can follow my process. What's the next step after you have the exponential? Switch them, because as soon as you switch them, you have created a logarithm. So instead of graphing this, I'm going to do log base 2. But notice it's base 2, it's base 2. It stays same base. So Give me one of the new, Brianna, can you give me one of the new coordinates that I should put over here in this chart? 1/4 -2. Perfect. Jordan, can you give me, Mr. Shank, can you give me another one? 1 gives me 0. D. Wait, what? 4 gives me 2. Jolene, what's the last little thing I better write down? Instead of y = 0, what is it now? X = 0. And now this is the big, scary part. You might feel a little bit awkward about this one. This is hard. There's a lot of stuff going on. So let's just ease our way into it. Let's talk about what happened to X. What the heck happened to X? Who has the guts to say what happened to X? What's going down inside my log? Asa, what do you see? It's the -3 is inside the parentheses, but is this minus right here, is that a multiplicative idea or is that a add and subtract idea? It's multiply. Multiply comes first. So this is first, that's second. So flip it over, move it to the right 3. So what happens when I flip this over? It's -1/4. What happens when I move it to the right 3? 2 3/4. Okay, what happens if I flip 1 over? It's now -1. Move it to the right 3. What is it? What happens when I take 1 and I flip it over and move it to the right 3? It should be what number? It should be, Abby's like, I think it's 2. You're right, it's 2. No big deal. How about 4? 4 became -4. Just -1, right? Okay, so we got that. And how about X = 0? Flip over X = 0. Still 0. And then move it over 3. So you've got a vertical asymptote at 3, which makes sense because where's 2 3/4? Isn't it really stinking close to 3? It's supposed to be. Oh, okay. Now let's talk about these. Oh, man. Oh, no, this is going to be hard. What happened to the Y values? That's these guys here and here. What's going to happen? We're going to take all of them and what are we going to do to them first is we're going to cut them in half, right? And then what? What happens if you cut that in half? Half of -2 plus 1 is 0. What's half of 0 plus 1 is 1? Half of 2 plus 1 is 2. You guys cool? If you play connect the dots, what should it look like? It's going to look kind of like this, or maybe because it got flipped over the axis, it actually may look like this coming down, but you can actually graph that and see if you actually did your points correctly. You guys think you can handle that? Let me give you time and let's have you do one of those on your own. And I'll give you about 10 minutes. So what you guys are going to graph is, why don't you graph twice the log base 4. So now I'm going with base 4, should be a nice easy value. And let's have you do 2x minus 1 and stop. Just that. Let's see if you can start with your exponential, go through the process of coming up with your data tables. Okay, so Ashley, can you give me the points that you would have used for 4 to the x? Yep. 0 is 1. And asymptote, that's the one, by the way, of all of these, this is the one that everybody forgets, but it's actually probably the most critical part of the whole story is that asymptote's really important. Monserrat, what makes it a log? Just flip them, yeah. So we got 1/16, 1, 0, 16, 2. Now, I was talking to Mr. Wheeler, and he didn't really like my presentation a lot. He likes to go straight to the log, but to me, is this cognitively difficult to write the exponent? To me, this is easy. Is it work to write all 3? Maybe it's a little time intensive, but to me, sometimes I just like things that are easy. I don't have to think very hard because I didn't have to do much. So, okay, well, shoot. Now what? Now what? Abby, oh man, what's going to happen to all the y values? Yep, so they're -4, 0, and 4. That was hard. Okay. This one's not quite so pleasant. Devin, what do we do with the x's? So what do we do then? So do we make that one 1/8, that one 2, and that one 32? Okay, remember what happens to things that are inside, everybody. That's really important. What do insides do? They're opposite world. Okay, so instead of, we're not going to multiply them by 2, what are we going to do? We're going to divide them by 2. So what does 1/16 become? 1/32. Yikes. And then, so 1 and 1/32. What does 1 become? A half. Move it over 1, 1 1/2. What does 16 become? 8, and therefore 9. And what does 0 become? 0 gets cut in half and then moves over 1. So if you could just plot these, do you need to graph these two? I don't think so, but do they kind of help you very quickly get over here? I think we played with graphing by transformation enough that you kind of probably have that down. So anyway, that's all good, but today's real lecture today, are you guys okay with the graphing? Are you all right with it for right now? So this is called properties of logs, and here is where I really have to make sure you guys are got this stuff down, because this is really why people did it. Properties of logs. Now, what you want to remember about this is that what a log is it's an inverse of an exponential, right? So when Napier did this, he was borrowing all of the properties of exponentials. We've done it already today. What was a square root? It was a half power. What was a cube root? It was a third power. Did we play with that? What's another little property of exponents that we used earlier today? What was a negative exponent? It was a fraction. It was a reciprocal, right? Well, there's a couple of things that we haven't done. See if you guys can remember this. If you have x to the n and you have x to the m and you multiply them together, what's that going to yield for you? What was the rule if you multiply things with the same base? What do you do to those exponents? You add them. Now, that's going to become a significant little detail to us today. What happens if you have things with the same base and you divide them? You subtract them. That would be x to the n minus m. Well, here we get into the new stuff. So, I will develop, boy, this got scooted over a long way. That's better. Okay, so here's my first property. If you have the log base b of m times n. Now, what could be, what is b? B is the base, and b can be anything I want it to be except for, can't be 1, and it can't be negative. That's really important because it's the same as the exponential. So this is what Napier when he kind of established this naturally comes right out of his definition. So this is kind of important. The log base b of m times n is the log base b of m plus the log base b of n. Now, I made reference to something about log tables, right? So this is what Napier would have done, is if he was working on a problem like the log of 7,000, now please understand what I just did. I just did the log of 7,000, which means it's going to be base 10, okay? Can you guys tell me, how could you break up the number 7,000 as the product of two numbers that are simple? Well, isn't the log of 7,000 log of 7 times 1,000? So what Napier would have done is he would have said the log of 7 plus the log of 1,000. Now, we did talk about this yesterday. What is the log of 1,000? So 10 to what power gives me 1,000? It's 3. Did we need to look that up at all, or we could just kind of do it in our head, right? Now, is that going to be an easy number? That one's not so bueno. That one's a little bit of a bummer. But what they would do is they would have a table that looks like this. And sorry, guys, online, I'm not going to bring it over. You can look up log table. So then what he could do is he could just pull this thing over and he could look up the log of 7. And so he found the log of 7,000 by looking up one number, a small number. You see it? That was fairly simple. So there was the log of 7,000, which turns out to be 0.845. This was 3. So what do you do if you put it all together? Is 3.845. So back at that moment in history, that made it a pretty easy thing. So what would you have done if you made it, say, the log of 50? They also would not have 50 in the table. What would they have? How would I break it up? I'd have a 10 and a 5. I'd have the log of 5. I'd have the log of 10. I know that the log of 10 is 1. And the log of 5, if I looked it up in one of those tables, is 0.699. So what's the answer? $1.699. Now, if I did this right, what do you think is going to happen if I took 10 and I raised it to the 1.699 power? What do you guys think I should get? I should get 50, but I want you to be very, very clear on this. I won't. Because these numbers are irrational. They're really, really hard. Why did I not get identically 50? Because I rounded this log 5. In those tables, did they have no choice but to round? They did. And in fact, back in the day, they had this thing called a slide rule. Talk to some of your grandparents and they'll say, oh yeah, slide rules. Yeah, I had those. And what they did is they actually had all the information on those tables on these special machines. Have you guys ever seen a slide rule? Oh my gosh. Let me kind of bring one of those things up so you can kind of see what happened. And let's give you an image of one of those. Oh my gosh, this brings a bad memory. I never actually had to use them because they were out before I got in school. That's not a good picture. Let's see if I can, well, this is good enough. I guess I'll do this. Let's do a new share. New share, it's going to be to this guy right here. And believe it or not, they had all of these things in there. All of the logs were in there. All the square roots were on there. The sines, cosines, and tangents was somehow on there. And they had to know how to move this thing around, and where the little lines lined up would give you the answers. Can you imagine that? Like, it's really hard even just to understand how to use that dang thing. We just had log of 7, and you hit log 7. On that one, you'd literally have to line it up and know how to read it. And we put people on the moon with that thing. So back in the day, this sounds terrible, but people that were really wealthy, they would actually have slide rules that were made out of ivory. They were very, very, very valuable because how precise are those things? They're phenomenally precise because they were used for all engineering. If they're building a bridge, building a skyscraper, building a rocket, it was all done on a slide rule. Which meant there's a lot of rounding that happened, but boy, they were very, very careful with how they behaved with that information. So I used to have one in here, but when we remodeled, I just finally got rid of it. It was actually hanging over there just as like a relic. I honestly don't even know how to use it, but they're just kind of a pain in the butt. I did it once in a class. But anyway, moving on. So the question that you might ask is, why does it work that way? Why, according to the rules that I've established with you guys, why is this the property? And I'll kind of show you how that works. So let's say that I had x is the log base b of m, and let's say that y is the log base b of n. Let's just say that's what I've got. Then I would know that according to this, can you guys help me write that as an exponential? How do I get rid of the log? We've talked about this a little bit. What's the base on it right now? B. So this would be b to the x is m. And what is this one right here? B to the y is n. And so what I'm going to do is I'm going to figure out what happens if I multiply m and I multiply n. What would happen, guys, if I took m and n and I multiplied them together? What could you do with that? This is a very simple proof, just establishing the property. What do you guys know happens if you multiply things with the same base? You add them. So m times n is b raised to the x plus y. Well, can I now, instead of going this way, can I go back the other way? Can I rewrite this? Can you guys help me out? How would I rewrite this weird thing as a log? What's the base of it? B. I told you that the answer is the exponent. And if we substitute in one step right here, what I said x was the log base b of m, and this was the log base b of n, and that's it. That's my full story. That was a pretty simple little proof. So if you see a multiply, what we can do is we can just break it apart. Now that's a little odd. So that's my first rule. You guys got that one down? So if somebody tells you to multiply, you're like, yeah, I don't want to. I'm going to break it apart as two problems that are adding. See what you guys think of this one. What do you think would happen if I divided two? There's a series of properties. This is number one right here. What's the next property? What do you think would happen if instead of multiplying them, I divided them? Minus. That's the log base b of m minus the log base b of n. That's number two. So far, so good, everybody? This one I feel a little bit less comfy with. Number three. The log base b of m, I guess I'll put a k there. I don't know. That may not be the best one, but I think I'll run with it. Log base b of m to the k. Well, isn't that m times m times m times m times m times m times m? What do you do if you multiply? What does it say? It says add. So this would be the log base b of m plus the log base b of m plus the log base b of m. How many times? K times. Oh, but what is repeated addition? Oh, that's weird. So if you follow the rules that we established, these are the big three properties of logs. So if somebody gave you something like that, you can just bring that down. Well, that all of a sudden makes some of the things that we did earlier yesterday kind of simple. See this? Oh, this is the log base 2 of 2 to the 5th, isn't it? Isn't 32 2 to the 5th? What can I do to the 5 according to this rule right here? Can I pop it to the front? And, oh, the log base 2 of 2 to the 2 is, the log base 2 of 2 is 1, so this answer is 5. You could have seen it here, but you could see it here fairly quickly. And so what we're going to do today is we're going to go through some of those properties of logs. I actually printed something out for you already. This is actually not your homework. This is just something so you don't have to write so much. But I do know that sometimes it's hard to slide these things into all right, there you go. So, off we go. Hopefully this will help it go a little bit quicker. So I tried to front load some of this before I just jump straight into this. So here we go. According to this, now in your homework, I'm going to ask you to do this some. I'm going to say, hey, expand that thing. So instead of saying the natural log of 3 times 5, what could I do to expand it? Well, that would be the natural log of 3 plus natural log of 5. Done. See how I expanded it? I took something, so in my table, I don't even have to have the number 15 out there. In fact, all I would need in my table is all the prime numbers, right? That's kind of interesting. How about here? This is the natural log of 4xy. So what could I do to break that down into individual little pieces? I'd have the natural log of 4, I'd have the natural log of x, and I'd have the you know what? But I'm gonna actually do something that probably the author of this particular thing, which I will say honestly I stole from somebody else, probably didn't intend. But what's 4? Isn't 4 2 squared? Oh, but that third rule that I told you is if I had 2 squared, I could bring the 2 in front. So one of the things about this is it allows you to break things down into the smallest little increments possible. That's pretty simple. But sometimes it really, really helps to tear things apart. Other times it helps to put them back together. So let's see. Somebody said this was all being added together. So can you guys help me put it back together? Instead of expand it, can we condense it? Can we contract that into a single solitary story? I've got a 4x, a 3x, and a 2. What should I do to all of those values? Oh, so what is 4x times 3x? Careful. 4x times 3x, 12x squared, times another 2. You guys like it? Pretty simple little idea. You can either put them together or you could tear them apart. Okay, rule number 2. I already went over this rule. What did we say division did? Was subtraction. So this is ln of 4 minus ln of 3. Sorry, when I downloaded this PDF, it looked perfect when I downloaded it, and then the bar got moved and I can't move it back. Irritating. That divisor should be right smack dab in the middle and it looks funny. So how about the, oh, see now this one is weird. This really frustrates a lot of students. This is the natural log of 7 minus the natural log of 6. You guys okay so far? Oh, this is going to really irritate some of you. Minus the natural log of x. I'm seeing furrowed brows some. What were 6 and x? Weren't they multiplied together? That's fine. You guys okay? Well, they were being multiplied together, weren't they? What do multiplications tell you to do? They tell you to add. Study that. Aren't they both together on the bottom? Oh, so here's what I do. I just look at everybody on top and I call it a positive. Everybody on the bottom, isn't it being divided? I'm dividing by 6. I'm also dividing by x. So although those are being multiplied together, notice the parentheses around it because they were together in the bottom, weren't they? They were together being divided, so I just distributed that out. So with that in mind, if someone had, hey, what about the natural log of 5 over 8xy? You just say the natural log of 5 minus the natural log of 8, natural log of x, natural log of y. I mean, literally, that's all I would do. All the ones on top, I make them positive. All the ones on the bottom, I make them negative. No big deal. So, how about this guy? How about if we choose to condense it? Where should the 3 be? Why is it in the bottom? Because it's negative. Where should the x be? In the bottom, because it's negative. Where should the 5x be? No, it's on the bottom together. So it looks to me like I've got this story that was 15x squared in the bottom. What was on top? 1. And you're probably going to feel like that's kind of cheap, but the natural log of 1 is 0. So it really didn't hurt to put that natural log of 1 in there because technically the natural log of 1 is 0 anyway, and so I haven't really changed my story. This was property 3. I already gave you that one, so we could just call this 3 ln 2, right? Because what did I say you could do with the exponent is you could pop it in front. How about ln of x squared? What would that be? 2 ln x. Now, I have a little bit of a problem with this one, and so I don't want to go too quickly through that. But what did I tell you early on that you could take the log of? You could take the log of any positive number you want, right? Told you can't take the log of a negative, and you can't take the log of 0. If I told you to take the log of x squared, since you're squaring it, what's x going to become no matter what I plug in? It's going to become positive or possibly 0. Unfortunately, when you do this, from here to here, I just changed the domain. Because now I can't let x be negative, but right here, could I have let x be negative here? This is really super picky, so guys, sorry about this. Technically, in this case, because of that domain, you should throw an absolute value on that. Sorry about that. That's a little obnoxious. And that allows me to do the following. So let's see if you can help me on the last one. Now that brings us a little bit more together holistically. This 2 ln x, is it positive or negative? So it should go where? Okay, study that carefully. Why is it now x squared? That 2 came back up, see? We were chopping it down, we're putting it back in place. What about this one, 2 ln 3? That's going to go top or bottom? Top. What can I do with the 2? Can I put it back? What's 3 to the second? Oh, okay. So just put a 9 there. And what's the last one? That's y to the 4th, isn't it? Isn't this y to the 4th because I could bring this back up? And where should it go? Top or bottom? Y bottom, because it's a negative, y to the 4th. Now over here, this is e raised to the 2 ln of x, which is e raised to the ln of x squared. Now I got to say, this is actually not in the properties that I've established for you yet, but there is a property that is almost like a sub-property that is the following. A raised to the log base a of b is b. A raised to the log base a of b is just b. Like, you just look at these and you're like, oh, this is the exponent, that's the log. They're inverses of each other. They kind of tangle and cancel out and you just get b. So this is e to the log base e of x squared. So you just get x squared. those are weird little problems. I don't really want to spend much time on them. Let's move on to the back. I'm going to go ahead and skip over example 4. I already showed you how to prove property 1. Property 2 and 3 are almost identical, so I'm not going to bother. So let's talk about, can we just do this great big thing and break it down? So I wanted to kind of go through these two, and then for today, I'm probably going to put that to bed and have you guys start on the delta mathing. So you look at this and you're like, oh man, that's going to be really hard. It's really not. Let's start with a log base 7. Where's the 5 right now? Top or bottom? Top. So it's positive. The log base 7 of x squared. Why did I put the 2 in front? Well, that was property 3, that exponents come in front. I'm going to go a little slower on this part because this is a little tricky. What is the exponent on that 2y minus 1? Oh boy, I hope you remember this one. See if anybody remembers. What is the exponent right now on that? Because you've got to look at it very carefully. It is to the 2/3, but what can I do with those crazy exponents? Put it in front. Now, can you see in some ways how logarithms might be kind of nice? You see how like a cube root, you're like, yeah, never mind, I'll just multiply it by 1/3. Isn't that easier? Multiply something by 2/3 and squaring it and taking a cube root? That's actually kind of nice. Where should 2y be? How do I handle that then? So then that's minus the log base 7 of 2 minus the log base 7 of y. You guys following me? What's last? Minus the log base 7 of x plus 1. What do I do with the square root? What is a square root, everybody? It's a half power. So where does the power go? In front. Okay, so here's your challenge. Try that one. See if you guys could pull that sucker all together. Now, when he says one fell swoop, you might have to put them all together and then finish it up and clean it up a little bit, but you can in one shot kind of do an awful lot of work. I hope this isn't too dark. This is going to be really dark. That's really dark. All right. What'd you guys do to the first part? 3L into, what is that? The natural log of 8. Where did you put 8? On the bottom. So 8's going to go down here. So that 3ln of 2 was just 8. How about 1/2 ln x? What is that? What happens if you bring that half up? What is a 1/2 power? Square root. Where should that square root go? In the bottom. So I've got a root x in the bottom. That's going to be this guy. I'm going to do that one pink. Where should 2 ln of 3x? Be super careful on this one. Anybody think you got it? What happens to the 2 when it comes up? What happens if you take this 3x and you square it? What do you get, everybody? Well, 3x squared, but let's simplify that. What happens if you take 3x and you square it? 9x squared, isn't it? It's not that hard. Just 9x squared. I wasn't trying to trick anybody, but what I wanted to make sure you understood is you didn't just square the x or just the 3. That came up and it actually squared both of them. And then the last thing, sorry, the purple was just really, really dark. I was hoping so people could see back and forth what happened. Where should this 2y squared go? It's going to go on the top, and I'm going to choose not to color it because if I do, you can't see. And so even though it says do this in one fell swoop, I'm going to go ahead and do this a little slower because could I cancel the 2 with the 8 here and make that a 4? And now I've got x squared, y squared, and I got a root x, and I'd be good to go. See, and that allows us to do some strange things because since this is a plus story, what could I do to the 2 values? Multiply. 2 times 32 is 64. Hey, and 4 to the third is exactly 64. What does a minus tell me to do? A minus tells me to divide. So that was the log base 2 of 16. I don't know how to do that one, and I don't know how to do that one, but when I put them together, I got it. Hey, 2 to what power is 16? We've done that one in here. It was 4. We're out. Now, common misconceptions. This is what screws people up. Does this look plausible, everybody? Look at it. If you look back at your rules, does that look kind of like what we did? Did you catch what was wrong? It wasn't supposed to be the log of x plus y. What was it supposed to be? It was supposed to be the log of x times y. Same thing over here. Please don't do that. It wasn't the log of x divided by the log of y. It was supposed to be the log, it was supposed to be like this, and that's supposed to be the log of x minus the log of y. So you got to be really, really cautious. This is a bad thing to do. Here, oh, see, that's a really, do you see how that's a little strange? See where that parentheses is? Parentheses matter. This takes the log of all of that stuff and raises it to the a power, whereas the rule that we had was the log base b of x to the a was this. What's the difference? See how here x has that power and only x has the power? Here the whole thing has the power. That's a little bit of an issue. So, and then the last one right here is, do you see how they brought that n down? Why is that? Can anybody tell me why that's wrong? Why can I not just bring the n in front like they show right here? That seems like the rule that I gave you. Can anybody see what's wrong with that? I do feel like this whole development is going a little on the quick side. What is wrong with bringing that n down? Yeah, the n, does a right now have that exponent? No, it doesn't. In fact, if I was going to do this, it would be the log base b of a plus n times the log base b of x, because only the x part had that exponent. Pretty dang important. So take out your stuff. I want you to go to your delta math, and for the next 20 minutes, we're going to just be practicing through some of those delta math things. It is a pretty lengthy assignment, but what I did is I killed the textbook assignment. I know this is not college for everybody, but it is college for a lot of you guys. And what I will tell you is in college, sometimes they say things are required and other times they say they're suggested. So in this particular story, I'm asking you to please do the delta math, but I am actually suggesting that doing the textbook would not be a bad idea. There's a little bit of that pull things apart, put them back together in the textbook, and it's listed in Google Classroom. You do not have to do it, but I would suggest it would be kind of smart to do. So for the rest of the period, let's just work, let's get some stuff done, and hopefully it won't be too hard.